Okay, we are in section now, we are in section 5.9, and we're going to talk about approximate integration. So approximate integration, up to now, the previous sections in chapter 5, you have found explicit antiderivatives for your integrals. Okay, and that's a lovely thing. That's a lovely thing. Okay, but sometimes you have situations, you have integrals, and in this case, these are two definite integrals. You have situations where it's difficult or even impossible to find an antiderivative. So, like for instance, the e to the x squared, the first integral, the integral from 0 to 1, e to the x squared dx. There's no known antiderivative for that function, e to the power x squared. And the second integral, where the integrand is the square root of 1 plus x cubed, the author mentions that the second function arises, second situation can arise when you have a scientific experiment and you have instrument readings or collected data. But so that's another integral that comes up where you cannot explicitly get an antiderivative. And if you can't find the antiderivative, how are you going to evaluate the definite integral? Well, what you have to do is you have to use what are called approximate, you have to do approximate integration. Okay, so how many remember back in Calculus 1 when you learned about an integral, if you want to find the exact area under a curve, and the fundamental theorem of calculus was developed by taking areas of rectangles under the curve and then summing up those areas of the rectangles as the rectangles become smaller and smaller, and then that produced the fundamental theorem of the evaluation theorem. How many recall that from Calculus 1? The Riemann sums. How many recall Riemann sums? Yeah, Gabriel remembers that, and John and Avery, and so those concepts are still valid, right? If we want to approximate an integral, we certainly could take the interval and divide it up into some. We can divide the interval up into some subintervals, like they do here in Figure 1, and then produce some rectangles, and the sum of the areas of the rectangles would approximate the area under the curve. So you see there in Figure 1A, they have what's called a left endpoint approximation. So let me go to the whiteboard here and sort of formalize that a little bit. Okay, so left endpoint approximation. All right, what I'll do is I'll draw an x and a y axis. And then, here's a function. Okay, and the function goes from A to B. Okay, and we're interested in the area under our function, under our curve, from A to B. So that's what a definite integral is, right? But let's say that we can't get the antiderivative for the function. So how might we then approximate the area under the curve? Well, what we could do is the following. Okay, we could, if we wanted to have 4 subintervals, okay, I could have divide that interval from A to B into two intervals, and then, divide a little bit more. And so I could call A sub 0, I could call that X sub 0. And then this point here is X sub 1, this point here is X sub 2, this point here is X sub 3, and then B I would call X sub 4. Nothing wrong with that, right? Nothing wrong with that. The question is, of course, how do we determine the heights of our rectangles? Well, what if I were to, like for the first rectangle, what if I were to use f of x sub 0 as the height of my first rectangle? Well, all right, so there would be my first rectangle. All right, so for the first subinterval, I used the left endpoint, the function evaluated at the left endpoint. Second subinterval from x1 to x2, what if I were to use the left endpoint x sub 1? Okay, well, if I did that, then, hold on here. You got to kind of f of x sub 1, that's fine. So, okay, here is my second rectangle. And I can keep doing this. I can keep doing this. For my third subinterval, I'll let x2 be the, I'll use that endpoint. Okay, and so if I do that, I get this. And then for my fourth subinterval, I'll use f of x sub 3. Okay, and so if I were to add up all the areas of these four rectangles, we would call this approximation L sub 4, and that stands. Hold on here. I want to make sure I have the terminology down right from the book, section 5.9. That's what we're in. That is called the left endpoint. That's a left endpoint approximation. A left endpoint. I'll have to hold on here. Got to give myself a little more room, right? Get better at erasing. So this is called a left endpoint approximation. And it's a Riemann sum, right? It's a Riemann sum with four rectangles. We're just picking the rectangles to be defined, the heights of the rectangles to be defined by the function values at the left endpoints of each subinterval. Now, we could also use the right endpoints. Okay, we could use the right endpoints. If we were to do that, let me go to and this is all in the recording. If we were to use the right endpoints, okay, Okay, we'd have figure 1b. See there in figure 1b how they use the right endpoints to determine the height of the rectangles. So we get a different approximation with the right endpoint approximation than we would from the left endpoint approximation. And then look here, if we go down a little bit, hold on, hold on. If we go down a little bit, we have a midpoint approximation. You see there where you have the midpoints of each subinterval, and those help determine the heights of the rectangles. That's another way to go. That's another way to go. So there are, I mean, it's no problem. You know, the problem, what we have to do is, of course, determine the values that we're going to be using for our approximation. Yeah, Jonathan?
Professor, what if you had, let's say, the graph of x squared where it's perfectly centered on the vertical axis? If you took the same left and right endpoint, like distance from 0 y, so -3 and +3, let's say, would it still be an overestimate or underestimate, regardless
Well,
of what
so,
method we used?
right, that's a good question. We're going to be, when we get our approximation, we do have to, it's a good question to ask, is our approximation an overestimate or an underestimate? We will be getting into that, Jonathan. I want you to keep that thought in your mind. We probably will have to wait till next class on Monday to get into that, but it is a concern. Yes, it is a concern, and unless like I'll show you a way to kind of help you determine that. I'll show you a nice way. Very good question. Very good question.
Okay, thank you.
You're welcome. Look here in figure 2. Man, they're using trapezoids. They're using trapezoids now. Instead of rectangles, they're using trapezoids. So a trapezoidal rule is kind of nice because the line segment connects the two functions. The function, I'm going to say it right, the endpoints have function values. The line segment connects those two function values. Basically the left and right side of the trapezoid get connected, and you can see it's pretty good. It can be pretty good. Midpoints are usually pretty good. Now I'll show you another approximation too while I'm at it here. Simpson's rule. There's a rule called Simpson's rule. Okay, so here in Simpson's rule, what you're doing is you so you divide your, you like from A to B, that's the limits for your integral, and you divide the interval from A to B up into subintervals. In this case, in figure 7, you have 3 subintervals, and for each subinterval, you use you use 3 points, and then the function values. There are 3 function values. Like for the first subinterval, you have p sub 0, p sub 1, p sub 2, and you pass a parabola through those points. Second subinterval, another 3 points. P sub 2, P sub 3, P sub 4, you pass a parabola through those 3 points, and so forth. So you see parabolas can approximate curvy type functions better than line segments do usually, right? So the Simpson's rule is another approximation rule that you'll encounter in section 5.9. And they actually go through a proof of, you can look at it, of how they get Simpson's rule, and then there's a formula here. There's a formula here for Simpson's rule. So I want you can look and see how the formulas are derived, but for the moment, I want us just to try an example. I'll mention one thing here before we get to the example. if you go into the blackboard, okay, hold on here. I gotta, one moment. Yeah, if you go into the blackboard and look under course content, chapter 5, click there. There's a section 5.9, approximate integration section. And there is a link there for a table of numerical integration formulas. Okay, so if you click on that link, it'll allow you to download a table of numerical integration formulas that I prepared for you. And what that table should look like is this table right. Hold on, is this right? Hold on. No, wait, that's not it. Hold on. Hold on, let me see here. Do I have it? One moment here. I don't think. Yeah, this is what that sheet should look like. And it gives, like for instance, the midpoint rule. It gives a formula for how to compute the midpoint rule and how to find the length of your subinterval. All right, so trapezoidal rules here, Simpson's rules here. Now this is not, these numerical integration formulas are for section 5.9. That's not on your first test. That'll be on your second test, okay? So let's look at an example here. Let's look at an example, because I like to try to get one in before you leave today. Okay, go ahead and copy this example down, and then I will go over it with you. Okay, we won't be able to complete all of this example today, but we'll certainly be able to find the midpoint rule approximation for the integral. We'll certainly be able to do that. Let me let you copy the example down. Okay, so we have here, so let me see here. So what do we have? We have the integral from 1 to 2 of e to the 1 over x power dx. Now, there's no integration technique that I'm aware of that can get an antiderivative of e to the 1 over x power. So that being said, we're going to have to get the value of this definite integral, we're going to have to use an approximation. And I'm going to use the midpoint rule approximation, m sub 10. So so I have an interval, right? I have an interval from 1 to 2. How many subintervals am I going to break that interval up into if I want the midpoint rule approximation m sub 10?
5.
So I want to approximate the true value of this integral. Hold on, almost right, almost right. Let me give you a hint here. I'm kind of underlining the answer here. M sub 10 means midpoint rule. You're going to use 10 subintervals, m sub 10. So what we have to do is we have to then figure out, okay, from 1 to 2, I got to break this up into 10 subintervals. All right, so let me go to the next page, and that's really, my view, the hardest thing. So, okay, in the next page here, I have, well, there's that table, right, of formulas I prepared for you. But let's go here to the solution. Here we are. All right, so here is 1 to 2. Okay. So 1 is equal to A, 2 is equal to B. And so what would the length of a subinterval be? Well, delta x is the length of your subinterval. So you're going to take 2 minus 1 and divide it by 10. And that gets you a 10th. Okay, so the first subinterval goes from 1 to 1.1. The second interval goes from 1 to 1.2. Third subinterval 1 to 1.3, and so forth. Let me give you a moment to copy this little chart here, or the graph, I should say. Please let me know if you have any questions. All right, so I'm going to make a little comment here. So you see here, like you have this x1 bar. What that stands for is the midpoint. So the midpoint between 1 and 1.1 is 1.05. That's x1 bar. That's the midpoint of the first subinterval. X x2 bar is the midpoint of the second subinterval. Well, the second subinterval goes from 1.1 to 1.2, so the second midpoint is going to be 1.15. Okay, and you can keep going here. The third midpoint would have to be 1.25 because it's halfway between 1.2 and 1.3. The fourth midpoint is halfway between 1.3 and 1.4, so that's 1.35 and so forth. So I think you can easily see what all the midpoints are going to be. It's really very beautiful math. It really is. Are there any questions on these midpoints? Okay. All right. Well, then now we want to get our approximation. So here is the formula. And if you think about the formula, it's delta x times the sum of the function values at your 10 midpoints. If you were to distribute the delta x through, okay, on all those terms, you would end up getting f of x1 bar times delta x plus f of x2 bar times delta x, and so forth. And what do each of these represent? Well, f of x1 bar is the height. That's the height of a rectangle, and delta x bar is the width of the base of the rectangle. So basically, the formula is you're adding up the areas of 10 rectangles, okay, each with the height determined by the function value at the midpoint for that subinterval, and then delta x is the width. Now delta x is 1/10, right? B minus A over n. This is n here. That's the number of subintervals you're going to use. That's 1/10. And then here are, I'm just writing out the formula. Are there any questions up to here, up to that step? Okay, well now let's remember what our integral was. Our integral was from 1 to 2 of e to the 1 over x power dx. So e to the 1 over x power is your function value, right? That's your function value. So when I say f of 1.05, that would equal e to the power of 1 over 1.05. When you have f of 1.15, that would equal e to the power of 1 over 1.15. And you have to do this for all 10 values. Okay, you have to do that for all 10 values. Normally in your homework, they don't give you more than 10 subintervals because it takes time. This is going to take time to compute. Are there any questions up to this step here? All right, all right. Well, now we have to evaluate all this. And WebAssign is going to want you to evaluate that, and it's going to give you an answer. So it doesn't want that's the answer it's going to want. It's not going to accept anything else. We have no choice but to evaluate all of this here. Well, what would be a helpful for evaluation on this? What would be a helpful? What would be very helpful? Of course, a TI 8384 calculator would be nice, but if you didn't have that, okay. I mean, if you didn't have, all right, yeah, sure. What program do you all seem to like to use that's free on the internet for computation? I'm sorry?
Excel?
No, no. You don't want to say that because can't use Excel on the exam, but good. That's a nice answer, Clea.
Oh,
But
Desmos.
how about another one? How about another one?
Desmos.
Desmos. Good, good, good. And Mohammed and Clea say Desmos. So let me show you how to do this in Desmos. So it's not hard. It's just it's a little bit tedious. But let me go here now. Now the answer we should get is 2.019.101.885. So like what would happen in WebAssign is it would say find the answer and round it to let me see, 1, 2, 3, 4, 5 to 9 decimal places. All right, so okay, let's see if we can get that answer. So we're going to use Desmos, or if you have a TI 8384 calculator, that's cool. But we're going to use Desmos to help us here. So let me go ahead and I'll come back to this page, but let me, are there any questions before I go to Desmos? Okay, well let me find the Desmos here. Here we are. Okay, so what I've done, I'm not done yet, but what I've done is I've actually, like a student would do, I've gone in and I'm typing in everything I need to type in. So 0.1 times, e to the 1 over 1.05 plus e to the 1 over 1.15 and so forth. Try it yourself. And yes, typing it all in, and all I have left is one more term, right? But try it for yourself and see if you can do it here in the last couple minutes here. Oops. Got to be real careful. I sure as heck don't want to delete any of this that I did here. So got to be careful. Right? Last term is e to the 1 divided by 1.95. Okay, now something's not right. Oh, look, I have a little error here. Should be 1.75. Okay. How about that? How about that? I think that's the answer, right? That's the answer that we're supposed to get. Let me see here. If, I'm curious. There's a chat. I want to see if any of you get that answer. Oh, thank you. Yes, thank you for catching that, Nihat. Yep, I saw that. But that's how you would do this kind of problem. Okay. Let me just give another minute. I want to see if maybe one of you, somebody else gets that answer. It's good to go through the experience of trying to get the answer. The question now, of course, is this an underestimate or an overestimate, right? And in the problem, we have found our midpoint rule approximation. It equals 2.019101885. But now what we want to do is, now that we have this approximation to the integral, we want to try to estimate the error in the approximation. I mean, that's really an important thing, right? If we approximate an integral, we'd like to know how good our approximation is. So let me go back to the thing here, because I know we're basically out of time here. So let me just finish up real quick. Are there any questions on this? Did anybody get it, or let me know. Hopefully, at least you see it. All right. So let me just go back to the problem here. Yeah. So what's left now are we have our midpoint rule approximation. Okay. And now what's left is, and we're going to continue this example on Monday. For Monday's class, we want to estimate the error of the approximation, and then we want to see if the approximation is an underestimate or an overestimate. So two very intriguing, interesting questions, and which we'll discuss on Monday. Are there any questions? Okay, I'll stop the recording.